What's that? Where is participants? People are rolling in, so I'll just welcome everybody. Good morning, good afternoon, good evening, wherever you are in the world. It gives me great pleasure to have Karen Christopherson speak to us today about early work to late work in the Columbia River Basin. But before I introduce Karen and the talk, just for those of you who are here for the first time, you're on a webinar with EMinar series, as we call it, which is webinars with roughly an EM focus, but we talk about other things as well, every Wednesday from October to June. And if you want to see previous webinars, you can go on the YouTube link or go to the EMinar page and you can register for upcoming ones. And we have 3 left in this series, 2 from Australia next week. Sasha Porgu on Mount Isa. The week after, Christine Chesley on work in New Zealand offshore. And then the final EMinar presentation is Kate Brandt on MT for Southern Australia. And then the very last EMinar of the season is an open mic where anybody can discuss anything for as long as we want, an hour, 2 hours, whatever. So please send in questions and we can organize discussions. An announcement, please, if anybody wants to speak or anyone got topics that we should think about organizing for season 3, starting early October, please send them to any of the organizers. So today we have Karen Christopherson. I've known Karen quite a time. I can't remember the first time we met Karen, mid-80s, I suspect. And Karen will talk to us about the Columbia River Basin in Washington, Oregon, and she'll tell us about the history. So I won't talk too much about it. Very quickly, you'll all have seen Karen's CV when you registered, and I don't want to take Karen's time away, but Karen's got a long career, started with USGS and BP, and then has since become a consultant and has provided services for 30 years. And she's authored numerous papers. So I'll just stop sharing, Karen, and hand over to you.
Okay. Okay, everybody. Well, Alan gave the introduction, and I think I first met Alan at an SEG in 1980. I was giving a paper and he was a co-chair with, I think, Bhattacharya. And that is very memorable to me because I think it was the first time I presented at SEG, and that also, as you'll see, sort of created a turning point in my life, giving that paper. Anyway, so today's saga is about mapping the Columbia River Basin with MT, and I was involved in this over 2 periods of time in the 1980s and the 2000s, and I interpreted a lot of MT stations, more than 5,000. This slideshow will show you about how we used MT and why in the Columbia Basin to map beneath the basalts. And this has never been shown publicly before. The reason for that is because there were a lot of different oil companies involved in both of the 2 sessions of acquisition and interpretation. And so that always becomes a bit of a mess to try and get permission. But just last November, I asked one of the geologists I worked for if I could show, results and not show particular things. And I was pretty excited when he said yes, because it is kind of cool, as you'll see, how we map the basin up here. And Washington and Oregon, and there's a lot of structural implications. So I think it's really important from a geologic standpoint or tectonic standpoint, and I hope that I can get permission to actually write a paper about this at some point. Okay, so why were we gathering so many MT stations and acquiring data up in the Columbia River Basin? Well, the answer is for oil and gas exploration. And why were we doing that up in the Columbia River Basin? So just a little bit of background for those of you that aren't familiar with geology up there in the northwest of the United States. There's this large flood basalt. Well, it's actually a series of numerous flood basalts that happened fairly recently, between 17 and 5 million years ago, and covered up a good portion of Washington and Oregon. And this is at the surface or really close to the surface over these states at present. Most of the flood basalts came out closer to 17 or 15 million years ago and covered up to 210 square kilometers of the surface. So here's all the different flood basalt flows that have been mapped from 6 to 17.5 million years ago. And like I said, most of the volume occurred earlier on. Here's just a map of Washington and part of Oregon showing you the coverage on the left. Most of the flood basalts came out of a dike swarm in southeast Washington and northeast Oregon. And then a lot of structural implications with rotation up in the northwest from plate tectonics, the Farallon plate offshore. There were some large lineaments and presumed some sort of lateral faults that occurred, and it set up a fold belt kind of in the middle of Washington there. And so a lot of structure, a lot of complicated geology, and much of it not well understood even to this day, as far as, what is the basement? Where did the accretion actually where's the accretion cut through this province and that sort of thing. So here's just a map to show you all this of the stress fields that were on the plate and the rotation. And you can sort of start getting the idea that that can set up a pretty complicated geologic scenario. And then let's just throw a whole bunch of basalt all over the top of this and try and figure out what's going on. So the interesting thing up here is that you have all these anticlines sort of running through the middle of Washington. And the minute that oil and gas geologists see anticlines, they can get pretty excited. Fold belts, there's been quite a few fold belts all over the world that have been studied and drilled and produced either oil or gas, such as over in portions of the Middle East on the edge of the southeast edge of, say, the Himalayas and that area, Papua New Guinea, Italy, Greece. So it's sort of a prime target because it can set up traps for oil and gas. So this just shows you some of the anticlines, and then there were grabens and the edge of craton. Well, that is sort of presumed. Again, a structural province that is exciting from a geologic standpoint, but also from an exploration standpoint. So in the Columbia Basin, this is just a sketch to give you a rough idea of what goes on. You have the flood basalts, which are shown in the dark orange. And then underneath it are some fairly recent, again, sediments that are clastics and presumably good reservoirs for oil or gas. There is a real lack of older sediments beneath the young sediments. And so there's some Cretaceous in the Swamp Formation, and then you go into basement. And as I said, nobody really knows exactly where or how the basement changes as you travel across the province. The wells shown there were all ones that were drilled before 1990. And from some of the subsurface data, then they could tell, okay, we've got a thick package of plastics down there underneath this flood basalt. And a few of the wells that were drilled actually penetrated basement. I'm not showing all of those on here. But they knew from these few wells that were drilled that there was a huge variation across the basement, and that, of course, there had to be some structural implications and possible oil and gas traps. So just showing you roughly here, what sets us up for the perfect MC scenario is we have all these flood basalts over the surface. Not real sure of the thickness of the basalts, but they had an idea that it could be from, zero basically to thousands of meters. And then we have presumed reservoir down in the Rosalind Formation. And again, you can see there's not much time difference. You have Miocene flood basalts for the most part, and then an Eocene presumed reservoir, and then older rocks, but not many of them, sort of a time gap there, and potential for the production or the source of the oil or gas down in the Swak Formation, because there's some coal beds and that sort of thing. Basement, mostly unknown, but was drilled in a few places. Okay, so how did I end up in this scenario? How come I ended up being a geophysicist? So when I was about 7 years old, my dad had a friend who was a mineralogist, and my dad took me along over to visit this guy, and he had all these cool minerals and everything. And I was just like, oh, this is so neat. And I decided I was going to be a geologist. So I went to high school in Boulder, Colorado, and I was pretty naive back then. Down the road in Golden was a school of mines, and I thought, well, that's where you should go if you're going to be a geologist. So I went down there and just walked into the admissions office and showed them my SAT scores, and I didn't even realize what they kind of meant. You didn't have the tutoring as a high school kid that you do now about what you should do in pre-college and all that. And so my SATs were 99.9 percentile or something. Anyway, so Mines offered me a full scholarship, excuse me, and off I go, 13 women in my class, 26 on campus, and something like 2,200 guys. Well, I wasn't used to this. I wasn't a party girl in high school. I was too busy with courses and studying and bands and stuff. And so my years at Mines, which were 2 full years with summer school both times, was a lot of fun, because I always kind of was into the guy stuff anyway, climbing, hiking, skiing, all of that. But it was really strange being a woman on campus, because all the guys knew who you were dating. When we'd go into the cafeteria for lunch or dinner, every head would turn, what woman's coming in. So I just got a little bit tired of that. And I transferred up to the University of Colorado in Boulder. So it's only 20-mile difference. And finished out my geology degree there. But in 1976 in the summer, I thought, geez, maybe I'd better get a real job, sort of an internship kind of thing. Sent out a bunch of applications, got a call from the USGS, and ended up in the field about 3 days later in Susanville, California, doing geophysics. So I really didn't know much about this, but we were doing telluric profiling at that point in time. And I loved it. It was really hard work, but we were traipsing all around sort of the Western US. And at that point in time, mapping the KGRAs, which were known geothermal resource areas. And the geophysics group in Denver at that time was tremendous. Frank Frischneck was the lead, and he was the nicest guy. Don Hoover, Adel Zodi, Dale Stanley, Mike Batzel. And so then I stayed on there working while I was in school, doing telluric profiling, AMT and airborne EM, and I just fell in love. So then, in love with geophysics. So then when I went to do my master's, I decided I'd do it in geophysics. And that was a pretty easy transfer because I'd had all the background at Mines in math and physics and stuff, and just took some more classes. And then I would drive down to Golden to take courses. You could do that in Colorado universities, the state schools. You could do a direct transfer of credits, and especially George Keller, who was sort of my geothermal guru at that point in time, and about EM and MT. And then I met a bunch of other guys who were in his sort of gang there, and many of them who went on to continue in EM and MT. I did a summer course in Iceland on geothermal, and then my thesis, which was supported by the USGS and the Colorado Geological Survey, was doing geophysics in Steamboat Springs, Colorado, which again was a lot of fun. So that was wonderful, and I stayed with the USGS till 1981. So back then, this was how we did AMT. We had a strip recorder, and we sort of like notch filters at various frequencies, and we'd record the E and H fields. And then one of my jobs as the sort of minion of the crew was to look for coherent events and actually measure the length of the signal, take a ratio, and then we multiply it by some figures to get an apparent resistivity. This was all scalar, and then we'd make maps and stuff of the resistivity at various frequencies and stations. So it's come a long ways. All right, so then at the USGS, we had done a couple of rounds of airborne acquisition EM over some of the geothermal areas to see how well that worked compared to doing ground studies, which were AMT, MT, telluric profiling. And when I gave that paper, and I think that's the one that Alan was there when he was co-chair, I got 3 job offers. I was pretty shocked at this, but anyway, they were from Unical Geothermal, and that was Don Watts at the time, Digim, Doug Fraser, and then Sohio, which was Standard Oil of Ohio, owned by BP. And BP was just starting up a technology center in San Francisco for, well, all geophysics plus computers, computer development, of looking for oil that was difficult to find, meaning in areas that are not seismically friendly. So we had this amazing group covering EM, MT, DC, IP, gravity, magnetics, borehole gravity, etc. And Ransom Reddig and Mike Holberston were in the group, among many other talented people. And the idea was to develop and progress technologies for oil exploration in the USA, but also abroad, because we'd become the technology center for BP. And we had a lot of money. I mean, it was millions and millions of dollars. And so we did a lot of domestic proprietary MT and EM all over the Western US, looking at places that were either fold belts or volcanic cover, limestone cover, that sort of thing. And we're able to support research by pretty much anybody that was trying to develop something along the lines of MT or controlled source EM at the time. And so there's a list. I mean, I met all these people, and everybody was so excited. It was a really cool time to be involved in the MT and EM field. So Ted Madden, Randy Mackey, Steve Constable, Che Bostic, and on sort of a who's who of the MTEM gang back in the early 80s. And at the same time, so we'd gotten to know David White because we were working with Francis Bostic out of UT Austin, and Geotools was suggested. David White, I'm pretty sure, came up with that name. And so our group helped advise and support and test the original Geotools. It was just really a lot of fun being able to develop programs, design programs, and work in the Western US, and then on some projects abroad. And so I guess Adam Schultz in his talk mentioned the MT Club, and I guess I'd be a member of that, as well as, of course, all these other people, because you really did have to know how to do it all. It was such a period of infancy that you learned every aspect of the theory, the acquisition, the processing, the interpretation, and I think I was really fortunate to be a part of that. So phase one of the exploration up in the Columbia River Basin came about because the price of oil had gotten very high in the late 1970s. There was the oil embargo, and people were very concerned, I guess you'd say, in the US, a little bit like now, about the oil source and having domestic production. So that was what drove doing this exploration in the US in places that really hadn't been explored before as an oil target. And the price of oil, right about at the beginning when we were starting this exploration at the Sohio group, had gotten up around $100 a barrel. So that was what went on, and that was all a lot of fun. It eventually kind of ended around the mid-1980s because the price of oil fell. But anyway, so getting into the Columbia River Basin, there had been some drilling there in the 1980s and prior for oil primarily, and most of it was done by Shell. And at that time, Shell and Exxon in particularly had very advanced technology groups, I guess something similar to what was developed at Sohio BP. And the easy target is like, oh, we'll just drill the surface anticline. And they really didn't have much geophysics. And those of you that are familiar with fold belts know that more often than not, in a fold belt structural setting, the actual target, the high underneath the whatever the surface is of the anticline, that's where your real target is. The anticline is not symmetrical all the way down. You have an offset one way or the other from the anticline. But anyway, sometimes they at least would get enough of an idea to know that they had some gas shows or oil shows, and then it was presumably a good idea to drill in that region. So meaning in this case, the Columbia River Basin. So just to give you an idea, there's the map in the upper left here, and this is just a series of wells that were drilled earlier on. So this is the center of Washington. You can see my mouse, and then you come down to the southeast, and then up in northern Oregon, there've been some wells drilled through the Columbia River Basalt. And this little cross section shows you how much the variation is in the basalt, which is in the gray, in thickness. So this is in feet. So the basalt's varying from, say, 2,000 or 3,000 feet down to 12,000 feet thick. And then the target, the Eocene clastics, again, a lot of variation in the depth to the top and the thickness of the clastic section before you'd hit basement. And then here basement has been reached in a few of these wells down at a depth from 10,000 feet or so, but even greater than 17,500 feet in this one well. So some of these wells were drilled before we started doing MT up there, we knew there was a lot of variation. And it's just like, you know, the question mark is, well, geez, what the heck's going on up there? How thick is this basalt anyway? So a lot of these surface anticlines, the relief on these anticlines can be a couple of 1,000 feet or more. I'm going to apologize. You'll see in this, I'll sort of keep switching back between feet and meters. And again, that's just kind of the way I think. So anyway, if you just even look on Google Earth, you can see these structures that develop and they're fairly parallel, but then there will be abrupt changes in them. And here's some of the wells you can see were drilled up on the top of these anticlines. And these are some of the older wells. And just to give you an idea of relief on these anticlines, which were produced by thrust faults, 2,000 to 3,000 feet on some of them. Pretty amazing structures. There's another one. So why MT? Well, it's pretty obvious, I guess, to us MT people. You have this thick resistor being the basalt, and it ends up being about 1 to 200 ohm meters. The clastics are 10 ohm meters or less for the most part. So good resistivity contrast there. Seismic was tried and for the most part not successful because of statics issues, variations in the basalt. Some of them would get kind of vuggy. Gravity, some problems there because you have the dense basalt, the dense basement, the less dense clastics, of course, but then there'd also be these inner beds. And so gravity wasn't very quantitative. Magnetics, paleomagnetic variations and that kind of thing. So as far as using mag for actually mapping depth and stuff wasn't very good idea, but MT worked pretty much perfectly given the scenario. So this well, just to show you, this was drilled in 1981. So this was just about the time we were starting the MT. And it was pretty clever because they drilled on a breached anticline. So it saved them a couple of 1,000 feet of drilling. And there were gas shows down in the sedimentary section, which are shown in that red circle. Now, at that point in time, they didn't really care about gas. They were looking for oil. But still, it was promising that you did have this production of hydrocarbons related to the anticlines in the fold thrust belt. So back in the 80s, early 80s, starting in 1981, so Ohio, one of the many efforts they had was to look at the Columbia River Basin, the basalts, and the sub-basalt structure. So a total of 1,552 stations were in the database. We ended up using a little over 1,400. And this was a set of various data, some proprietary and some non-proprietary. And so Ohio acquired 776 proprietary stations. And then there were these group shoots, as they call them, or non-proprietary surveys done by a few companies such as Geotronics, Phoenix, Z-Axis, which had been Woodward Clyde, and then we traded for a few stations with another oil company. So this is a little video to show you kind of how the project progressed. And so you see Washington and Oregon up there in the northwest of the US. And we will zoom in and see the fold belt there along the Columbia River. So there you can see the folds, thrust fold belt, thrustings from south to north. And one of the first surveys, because nothing was known, was these little red stations. They were doing one set of stations per every township, which is, township is 6 miles by 6 miles. We couldn't acquire data on the Hanford nuclear, which was purple, Yakima Training Range blue, Yakima Indian Reservation pink. The yellow stations were the Ohio stations. So we start with a grid that was pretty widespread and then go in with a close, dense spacing over presumed targets. Blue stations are some Phoenix surveys, again, sort of extending the looser grid. So that was the data set we ended up at Ohio. And we were able to cover most of the flood basalt territory with that. You know, we wanted to make sure that we went to the edges basically of the basalt where there was basalt on basement and get a good feel for constraining the basin. So you have zero thickness of sediments between the basalt and basement, and then going into the deeper portions of the basement and focusing on 3 prospective areas at that time from what we had. So this was the early years of commercial MT, and most of it was remote reference. So Z-axis, Phoenix, Geotronics. Some of it was hardwired, some of it was telemetered. The mags were both coils and squids. Squids, there was a big controversy at that time, like which one's better, this sort of thing. And the MT gear was pretty similar to today, but multiple bands for sure of recording. And of course, the coils were probably twice as big as they are now. And of course, the processing is better today. The data quality really varied. A lot of the Geotronics data just weren't that good. And I don't really know why. You know, we had the luxury at Ohio doing a lot of tests and, you know, testing coils versus squids or various layouts, remote reference, which was very new at that time. But anyway, so some of the data weren't so good. Here's I was sort of showing you one station that's pretty good on the left and a station on the right that's not so great. To give you a clue of some of the stuff, the way we were looking at things, skin depth was actually plotted across some of the contractors' plots. Again, this is early days. We didn't have a lot to go on as far as interpretation. Data quality, good stations, bad stations. And again, our whole data set, we had the holes in it because Hanford nuclear site, there was no way we could get on there. The Yakima Training Range is active military range with stuff that blows up. And then the Indian Reservation, they were not interested in letting us on the property. So that was the whole data set. Noise up in Washington and well, the Northwest, there's the Bonneville Power Administration, which has a lot of large transmission lines and dams. And so here's a shot, an aerial shot to show you some of the transmission lines and another one with a dam and some transmission lines. And the noise was not as bad as you might think, but it really messed with the tipper. And we didn't really see any bias in the amplitude and phase like you can from the DC lines. These are all AC. But anyway, that was just another thing we had to deal with, you know, try to get as close to the transmission lines as we could, though you're going to sacrifice some stations. Interpretation, well, it was all 1D. And it started, you know, Bostic inversions. That was what was used on a lot of the early interpretations out here. And then finally, we got a layered 1Ds. 2D, we didn't have that available when we did all this work out there in the 1980s. When we did get 2D, we had this big computer center at Ohio, and you would run the 2D overnight. It would take like 10 hours to do a simple 2D inversion that now, or 2D forward or inversion that now you can run like in a minute or whatever. So the very first job I was on was in the winter of 1981. There was probably 4 feet of snow on the ground. And anyway, it was just 13 stations or something. And I remember it being at my drafting paper and drawing a cross section on graph paper with the 1D models. And so I made this up on Geotools, but this gives you an idea of this was, you know, how you interpreted data back then. Anyway, the lucky thing was that a lot of this basin is pretty 1D, at least to the top of the basalt, and even a lot of places to the basement. You start seeing divergence between the two MT amplitude curves as you get deeper, and a lot of that's coming from the fact that you have this big basin and current flow sort of circling around the basement. So this was the final product out of that. And this is the basalt isopack. And you can see that the thickness of the basalt is getting up around, say, 15,000 feet. You know, so between, well, not quite 5,000 meters thick. And then this was the sediment isopack, and the sediment's getting up around 15,000 feet, approaching 5,000 meters, say. And then, let's see, to the basement elevation. And so the depth to the deepest part of the basin is down greater than 24,000 feet, or say 7,500 meters. So that was what we ended up developing around 1985, 1986. The price of oil fell around that time. A lot of our projects stopped, and some people were laid off around 1987 out of our group, which was unfortunate. And I got shuttled into seismic for a year, which I didn't like. So anyway, in 1988, Ohio wanted me to transfer to Houston. And I hated Houston. I still don't like Houston. Apologies to anybody that lives in Houston. And I said no. And I didn't really know what I was going to do, but I was going to move to Alaska and print T-shirts with polar bears on them. So Ohio gave me a very nice severance package. But the next day, I had a call from BP Australia, and I'd sort of tried to latch myself onto this project in Papua New Guinea because I wanted to go over there and go scuba diving. And so they wanted me to help them on exploring in PNG. And I said, well, I'm not with Ohio anymore. I just quit. And they said, okay, well, we'll hire you as a consultant. So that's how my consulting company started. Moved back to Colorado, up to Evergreen. And since then, I've worked on all sorts of projects for almost any resource you can look for. And I spent 8 years, better part of 8 years working in PNG, and then a whole bunch of other places all over the world. It's been very exciting, but a lot of travel. I married an Australian helicopter pilot in 1988 that I met in PNG. We were living in 3 places. We were both working overseas, so we would just meet up. You know, we'd meet up in London or Cameroon or whatever, and it was crazy, but it was a lot of fun. Anyway, finally, that was too much. And so then in 1996, I married my now husband, who's wonderful. He was a commercial diver. Anyway, so my career, I've had a lot of fun and worked for a lot of interesting people, some more interesting than not. But anyway, it's been great. So how did we get to another round of exploration in the Columbia River Basin? Well, in the early 2000s, the price of natural gas went up. So now there was a sort of a flurry of of gas exploration. And I got a call from a geologist who had worked for Amoco, and somehow he knew about the work that Ohio had done in the Columbia River Basin, and just had me come into their office in Denver and tell them what I knew. Well, I happened to have kept my report that I wrote for Ohio. I guess I probably shouldn't, but I did, just because that was such a big kind of cool project to show what MT could do. So I went into their office and they said, let's reconstruct this. So in the early 2000s, this looking for gas, there were a lot of the oil gas companies were getting involved. And now the thinking was a little different. They'd learned a lot from working on basin-centered gas in Wyoming. So that it wasn't just the geologists, it was the drilling engineers and that sort of thing about how to produce this gas. And so they were looking, in this case, in fold thrust belts for the deeper structures that were offset from the surface anticlines. And MT, of course, comes into play. We have these areas with volcanic limestone cover or an overthrust situation where you've got even Precambrian and placed over, say, Cretaceous sediments. So because of this advance in drilling technology, then this one small oil company in Denver was looking at Washington State, and some of the wells that had been drilled in the 80s, they realize now could be produced as a gas well from this knowledge gained in drilling in these areas where primarily before they were looking for for oil and just didn't understand how you could produce the gas. So these were some of the wells drilled prior to this time, so drilled prior to about 2000. And the gas shows are shown with the green circles. And then you can see that the depths of some of these wells were getting down to 16,000 feet, 17,000 feet. So the basement is way down there, and you have these gas shows that are pretty deep. But the price of gas was high enough that this was an economically viable play. And also there's a major gas pipeline that runs pretty close to the area they were interested in, Washington. So again, MT, obvious choice of exploring out here. And the little diagram just shows you the resistive Columbia basalt, somewhere between 100 and 200 ohm meters. The conductive sediments beneath it, 10 ohm meters or less, and then basement around, say, 1,000 ohm meters, whatever. So good contrast. So we had to reconstruct the data set that we'd done at Ohio. So it was sort of a data hunt. And luckily, Ohio, Guy Flanagan was the head when I left of our group, and he'd had all of the Phoenix data converted to EDIs by the Geotools group, so Arnie Orange and the people that worked there. So we had about half of the good proprietary data as EDI files. Then the rest of it, we just went hunting around trying to find it. We did find the Geotronics data, which a lot of it wasn't very good. And we had paper plots of that. We had paper plots of the Z-axis, some of those data. And so then for the non-digital data, we actually digitized the phase and amplitude curves. Then a whole bunch of new exploration started, driven mostly by the companies shown here. So Savant and Canna out of Canada, Trident out of Canada, Excel and Delta Petroleum. So here's some of the data that we acquired in the early 2000s. Nice data. You can see some high tipper data there in places. And again, this is from those transmission lines. Here's some stations just to show you how far away or how close we could get to the transmission lines and get decent data. But even where you see the high tipper, the amplitude and phase don't seem to be showing bias. And so a lot of these were usable. And I showed you this before, but turns out if you just map the tipper at various frequencies, you could kind of come up with a map of where the transmission lines were. So we rebuilt this Ohio data set as much as we could, buying the data so that it was all legal and everything, and then did proprietary acquisition with these numerous companies or clients. So this was the whole data set in the 2000s. So I'm just going to show you the various data sets. So the idea was that we used this Ohio data to get sort of a rough idea of what was going on in the basin, and then started doing sort of denser spacing, but then each client would start doing closer spacing of the stations up to say maybe 500 meters apart when they had prospective areas or they had the lease in that area. So those were the Phoenix data. The orange are the Ohio data. And then we start getting the various data sets brought in here. So you can see this is getting pretty dense here. It was really fun, actually. I mean, to be able to go out and just acquire data how you really wanted to do it. And so let's go back there. So that was the data set, the various clients. Still no data on the Yakima Indian Reservation. There were some stations on the Hanford that were recorded in the 1880s, so we had a little bit of idea what was going on in the Hanford nuclear site. And then up at the Yakima Training Center, the Army site, they actually allowed us to go in there. And they would call the crew every morning and let them know which part of the whole training center there wasn't going to be active shelling on. But we actually were able to get there. So for the 2000s data set, there were over 4,100 MT sites used. More than 4,600 were available, but I showed you earlier some of the data quality from the 1980s just wasn't worthwhile. I'm getting an unstable internet thing, so I'm gonna stop my video right now. Well, no, I'm just gonna turn off mine. Well, never mind, I'll try it. Okay, so a lot of MT data had been acquired in the 1980s, but we couldn't find it, or it had been on old tapes that had gone bad, had been destroyed, lost, etc. And because so many people had acquired data in the 80s. So we ended up covering about 74,000 square miles up in the Columbia Basin with MT. So the contractors back in the 80s were the ones I mentioned earlier. And then from in the early 2000s, it was all Geosystem who became Western GECO. And in the 2000s, so I mentioned this, we had EDIs from some of the 1980s data and of course all the new data. And then we'd had to digitize some of the old data. We did a lot of experiments we went back and recorded stations on or really close to where we had data from the 80s, just to see the repeatability. And it wasn't bad, you know. Of course, now we have good processing and then good post-processing routines, and everything else is just better than it was, you know, in the 80s. So the original interpretation I did on WingLink. So then when I got permission to do this talk, I transferred a lot of it over to Geotools, but I don't even know how many 2D profiles I ran for this project. I mean, basically we had 2D profiles going through all the different sets of data that we had there in Washington. And this is just showing you one example in the lower left. There were 3D model versions done by Geosystem using Mackey's code. I put some of them over the map there on the right, just to give you an idea. A lot of times we'd run two different sets of the 3D inversion, like if we got more data or we wanted to focus on a certain depth segment or that kind of thing. So it was just a huge difference in the interpretation between the 80s and the early 2000s. This is just an idea of one of the cross sections. This is actually a little bit older to show you how this base changes in a cross-sectional view going across a wide swath of it. This is vertically exaggerated, but you get the idea from where you go to no sediments between the basalts and basement to where you get these just enormous changes and sort of big piles of sediments. This is just one of the profiles. I can't show a whole bunch of this stuff like I'd love to be able to do until I have better permissions. So what I did was I put the wells in here as 1Ds. So the 1Ds showed the base of basalt that was drilled in the well, and then the top of basement. So basalt's the sort of medium blue, basement's the dark blue, and the clastics are the orange. And this is a section out of either probably out of a 3D inversion. And just another one. So this one in the middle there, you can see that shell on BN19. So that gives you an idea of how under these anticlines, the thrust action can double up the section of basalt, but then also create highs on either side of the anticline. This was just one area. This was one client's prospect area where you can see all the MT stations. And the main way we did the exploration here was to map the structure, the base of the basalt, and then map top of basement. So you could look for highs. Basically, you'd want a high on base basalt and look for four-way closure was ideal, of course, three-way closure, and then site a well. 3D models. I now just recently Geotools has the new 3D scene thing. So of course it's very cool to put all the stations in there and zoom around on the 3D inversions. So this is the final result from the 2000 work. This is the elevation on sediments or base of basalt. And you can see this elevations varies where the top of the basalt, the top of the sediments get down about, say, minus 5,000 meters in elevation. And that line running through there is just an approximate location of one major linear feature up in Washington called the Olympic Willowa lineament that a lot of people talk about. But when you look at the results of the MT, you can kind of see this tear through the basin where you can see a few. And this is one reason I'd like to be able to have this more public, because the people that study this stuff, see if they could understand better about these lineaments, possible left lateral motion offsets in the subsurface created by all the various structural episodes up in the northwest of the US. This is the sediment isopack. So how thick are the sediments? And you can see they get pretty thick there, up to almost 5,000 meters thick. The elevation on basement, so deepest part there about minus 9,000 meters. And again, just to kind of relate this to you, over on the lower right, you can see the little black line showing you that's about 50 kilometers. So mapping over this huge area, and these have been smoothed a bit, of course, because we're looking at such a tremendous area. But the features are all pretty well documented as far as not being single site anomalies or that sort of thing, because we had so many stations. to map the deeper part of the basin, in particular, central part of the basin. So this was the final sort of area we covered. The orange is the coverage of the whole of the flood basalts. Again, we were focused on the area where you could have oil and gas, hydrocarbon development, and also a lot of the structures present, the anticlines and that sort of thing. And then I just kind of drew that Olympic presumed owl Olympic little liniment in there. And then here's this little video I made showing you the so the base of the basalt and the top of the basement and zooming around underneath it and sort of give you an idea of the relief in this basin. It's pretty amazing, I think. All right, so to summarize, 2 rounds of MT acquisition up in Washington and Oregon, more than 4,000 MT stations of good quality data. We mapped the structure of the Columbia River Basin using MT and structurally the growth of structures along faults, presumably, and features like various lineaments. I'm not a tectonics or deep structure person, but I think these data could be used to bring some insight to those features. At least 9 of the 11 wells drilled. So there were more wells drilled in the 2000s. And then the price of gas fell. So the project ended in about maybe 2006, 2007. But anyway, the wells and MT agreed really well at all of them, except one in particular, where there were a bunch of inner beds in the basalt of a tufaceous or clastic material. And they weren't thick enough that you would map them with MT, but they were there. And so that sort of screwed up the interpretation. But for the most part, it was the MT and the actual subsurface data agreed really well. The basalt's as thick as 5,000 meters. The basement's as deep as minus 9,000 meters. The MT mapped about 85,000 square kilometers. And it was a fun project. Anyway, thanks for listening. And I think I've approached Alan's favorite time for me to not exceed. So I'm done.
Oh, thanks very much, Karen. Absolutely wonderful to hear the history. And I think it's great for, people entering MT these days to see the challenges that we had in the 80s. But the other thing, I guess, that struck me was that a lot of the information that you got out of the 80s data has stayed robust. That even though the data were pretty poor, you were still able to get robust information that stood the test of time.
Well, you know what else is interesting is that if you compare the 1D completely 1D inversion from the 80s with the 2000s, it kind of looks the same. So using those data from then, and because the structure was a lot of it very 1D, it's sort of cool in a way. And also that a lot of the data in the 80s was actually pretty darn good.
Yeah, brilliant. It's while we wait for questions, please throw your questions in the Q&A for Karen. And is there any chance that these data might enter the public domain?
Yeah, I meant to mention that. So gosh, back I think around 2010, maybe 2008, and I don't remember exactly how it came up, but Adam Schultz, Earth Scope, whatever it's called, he kind of linked up with us, and we got permission from one of the Canadian companies gave the data to OSU. So that, I'm not real sure exactly what Adam or how you access that. Because that was easy. It was a smaller company and we could just get permission to do it from that company. And that's another thing I kind of have in my mind, is to see if we could get any more of it released. And so once I'm going to go back to my friend at one of the companies and see what we can do about that and get it somewhere out there. And I mean, if anybody has the best depository idea for this, if we could get it released, then let me know. But that's my intent, Alan. I mean, I think this is a really cool data set, and I don't want it to just sit there and all go away like the 1980s data did.
Yeah. Now, one thing, I've run a few of these 3D comparison workshops, and I think we're still at early stages with 3D, although possibly Randy would complain about that. But I do think that still all the different 3D codes approach inversion in such different ways that really we should be using more than one code on our data sets in order to explore model space more effectively.
Yeah, well, I always run 2D just because you can. So I then always compare 1D, 2D, 3D, and just I look for anything that is really dissimilar. But in this case, again, because it's not hugely complex structure, I think the 3Ds worked really well. Anyway, the interpretation that you saw was a combination of 2D and 3D.
Yeah, we have a question from Jade Crosby. Very interesting talk. Loved seeing how historical MT data was acquired and processed. In the 80s, how were transfer functions computed from analog time series?
You want to answer that, Alan? You probably know better than
I think you did. You said you measured the amplitude, right? You just did yeah. You measured the amplitudes of the two spikes.
Yeah, that wasn't done that much. I mean, that was AMT data.
Right. Right.
I'm not real sure like what Dal Stanley was doing, because I was only involved with the AMT side. So anyway, yeah, but that was laborious young geophysicist work.
Yeah, I'm sure a lot of the broader band MT was, like I did for my thesis, was on paper charts, and you hand digitized the time series.
Okay, so you did that. Okay.
Yeah, and then you used Sims et al. Equations to calculate the transfer functions. Okay, we have a question. Could everybody please send questions in the Q&A so I don't miss them? But we just had a question in the chat from Didas Makoye. Excellent presentation, Karen. Do you have any hydrocarbon discoveries in the surveyed area? Did you recognize any major differences between 1D, 2D, and 3D inversion models?
Well, the answer on the discoveries is yes. They had gas that could be produced at probably 3 of the wells, but then the bottom fell out. You know, as you know, resource markets can be so up and down. And when you're doing a survey like this, they knew what their gas price had to be what the gas price had to be for it to be economical for them to produce. And near this, or well, the reason the project ended was then the price of gas fell enough that trying to produce the gas and get it to the Henry Hub in Washington was not economical. So typical of a lot of oil and gas plays that are in more difficult provinces. Did you recognize any major differences between 1D, 2D, 3D? Well, of course, the 1Ds versus the 2D, 3D, by the time you got to basement, you'd see a difference. And so definitely didn't try to rely on the 1Ds for any final interpretation, especially on basement. I would just look at the 1Ds and see, okay, do they kind of look like the 2D, 3D? The 2D and 3D, the only difference I would see really, and I'd ask Randy about this, was the resistivities would vary, like where you would pick a horizon. But for the most part, they agreed reasonably well, unless there was a station stuck on a 2D profile that had a lot more 3D features in it. But in this area, it was not one of those places that you really noticed a lot of difference, just because that's the way the geology is for, in the most part, let's say 90% of the basin.
Yeah, talking to Randy, he asked a question. Hey, Randy, great talk, Karen. Did anyone ever go back and try seismic again with more recent technology to see if it worked better?
The answer is yes. So Shell was involved also in this in the 2000s.
Mm.
And so they had set up a big program over some of the original anticlines, like Saddle Mountain and that. And I think I remember right, they just vibed it to death, but the parameters were a lot better. So one of our permitting team, I mean, we had a team of permitters that were amazing, was a seismic guy, and he got to see some of the, the records, and they were getting fairly decent data. And this is through really thick basalts. So they were going north on these parallel lines across this anticline. And they got up there, and there was some Indian sacred grounds, Indian, that we really didn't know about. But anyway, so that was shut down because of cultural land reasons. So they didn't get to finish that job. But not unlike in New Guinea, the same thing happened, where we were over there working for years because seismic, not only was it really expensive, but it was really difficult because of a similar thing, these vuggy limestones. And Exxon solved that problem just the way that they would cement geophones and stuff in. So the answer is yes, it's still expensive, but they did get some decent records.
What about ambient noise seismology? Has that been tried yet? That's been successful in some of the basins.
Yeah, there is some of that available. It's kind of scattered. I could have shown a map of that. So it tends to be along some of these older fault lines and deeper part of the basin. But as far as it being sort of consistent where you could use it around the basin, from the maps and stuff I saw, it wouldn't be consistent enough.
Mm-hmm. We have a question from Andy Calvert. Hey, Andy, great to see you here. Andy's a seismologist. So, great overview of the basin. Could the northwest-southeast oriented offset seen in the basin structure be the Olympic Wallowa lineament, which is interpreted to be a major strike slip fault system discussed by Tom Pratt in his 2012 GQ paper?
Yeah, that's what I think very much so, because if you look at the MT and you look at it in a little more detail, it looks like you can see I think it's left lateral movement, but that's one reason I'd like to be able to get the data or interpretation out there. And for some of the people that have been studying the basin more from a structural aspect for a long time, there's this geologist, Steve Rydell, that's sort of in our generation, Alan, and he's like his whole life is the Columbia River basalts. And so that some people could maybe get some answers to this, because there's even controversy over if the Olympic Wallowa lineament is a real thing and some of these other lineaments and fault systems. But it sure looks like that the MT is mapping that.
Jerry Roth sends a question in the chat. Karen, thanks very much for excellent recounting of the history of MT development and deployment, especially in the challenging Columbia Basin. Of course, your key role in much of it. Going back to geoscience and geotectonics, with high oil and gas prices, could you see yet another phase of exploration?
Yeah, maybe. I think, one difference now is that, well, in the US and Canada, so our buddies up in Canada, we've found a lot cheaper ways to produce oil and gas. Mm-hmm. But if the price of gas, I don't know, even if the price of gas went up, there's so much cheap gas available now that I just don't know that would happen. Jerry Roth's another guy that goes back. I first met him way back.
Yeah.
Parties back when FCT parties were a lot of fun.
Yeah. I hear that the Europeans are looking for gas right now. So. Okay, if there's no more questions from the audience, thanks very much again, Karen. Absolutely brilliant overview of 40 years of work. And see everybody next week. Bye for now.
Thanks a lot.
Bye.